Thank you very much. My name's Nick Billam. I'm Director of Policy and Communications at the Geological Society, which, as you've heard, is just through those doors there. Hopefully we won't have to go through there this evening. But it's a great pleasure to welcome you to the Royal Society of Chemistry this evening, and a particular pleasure for me to be involved in an event relating to a topic in which both our sciences, chemistry and geology, have such an important role to play, and to be involved in a collaborative project between our two societies. And as you've already heard, there's more and more of that sort of collaboration going on around this fantastic courtyard. It's a really welcome initiative. As I mentioned, I think shale gas is a topic where geology, chemistry, other natural sciences and social sciences and engineering all have an important role to play. And I think that this sort of publicly contentious issue, where science has an important role to play, are also vital areas for our organisations to get involved, for scientific societies like ours to play their role. It's a societal matter really to ask whether shale gas should be got out of the ground, under what circumstances, how that should be done. But we've got a really important role to play in nurturing and supporting the research communities, and then in making sure that that research actually gets picked up and used in public discourse around these contested topics, which can be very polarised and aren't necessarily characterised by being very well informed, and indeed political decision making. You could make the same sorts of comments. So it's an important role, and it's not one that's always easy, and it's very good to be able to work across our societies to do this sort of thing. An initiative in which the Royal Society of Chemistry and the Geological Society have got an interest, and an initiative which we're both supporting, is a research consortium called REFINE, Researching Fracking in Europe. And Professor Fred Worrall, tonight's speaker, is one of the main researchers in REFINE. And I wanted just to take this opportunity in introducing his lecture to say a little bit about REFINE to those who haven't heard of it. It's an innovative approach. As a grouping, as a consortium, it shares the approach of my society and of this society of focusing on trying to understand what we can about the relevant science, getting the research done, and then communicating that research in an impartial way. And that's a really important role to play in such a contested area. The thing which is particularly novel about it is how it's funded. The funding for it comes from a variety of sources. There's funding from the Natural Environment Research Council, one of the public research funding bodies for some of their initiatives. There's some funding from the Environment Agency, but most of the funding actually comes from oil and gas companies who are interested in extracting shale gas, exploring for shale gas. And it's a genuine attempt to address a dilemma. Very often, research which is done by commercial companies is questioned. It's probably fair to question research which is done by and paid for by the companies who stand to benefit from the outcomes of that research. On the other hand, there are legitimate questions raised by members of the public and all sorts of stakeholders who want to see their questions answered and want to see research done to address those questions. And there's a strong argument to be made that those questions should be addressed and the research should be paid for by the companies that stand to make commercial benefit from it. So REFINE is doing a fantastic range of work, a variety of research projects going on, and the innovation is to have a completely independent science board which determines the research agenda. The funders have absolutely no say over the research questions which get addressed and how that research is then questioned and is then communicated. And the role of the Royal Society of Chemistry and the Geological Society and other supporters in this is to keep the process honest. So we meet regularly and look at the procedures in place and make sure that there is that genuine separation between the funders and the setting of the research agenda. And it's the sort of model I'd really like to see taken up in other contentious areas. So it's a great pleasure, having put in that little plug for REFINE and for that interesting model, to, as I say, introduce one of the main researchers with REFINE, Professor Fred Worrall. He's going to speak to us tonight about exploring the impact of the unknown, a potential UK shale gas industry. Now, with the prospect of a shale gas industry developing in the UK, we need to try to understand what impacts it may have on the UK environment and the global environment in advance. We've got some time to do this, to explore whether we can prevent, avoid or mitigate against potential impacts prior to the starting of such an industry. But there's a question. How can we understand the potential impacts of an industry that does not yet exist? In this lecture, Professor Fred Worrall will consider several approaches that we can take to understand the effect of something that has not yet happened. These include learning from the US's experience and potential mistakes, and considering the impact of comparator industries within the UK. For example, why a sewage treatment works might be considered as being like a shale gas well pad. He will also consider current work measuring impacts of the onshore oil and gas industry and the historical records of pesticide pollution and what they can tell us about what might happen if fracking takes place. Fred is Professor of Environmental Chemistry in the Department of Earth Sciences at Durham University. His research interests include agricultural pollution, carbon biogeochemistry, contaminant hydrology and environmental chemistry. His current research includes addressing the fugitive emissions from onshore gas infrastructure. Fred was one of 30 scientists who took part in a workshop held in Washington last November that brought together scientists from the US and the UK to better understand the potential environmental impacts of unconventional hydrocarbon extraction. The workshop was supported by the Natural Environment Research Council in the UK, the National Science Foundation in the US, and the Environment, Sustainability and Energy Division of the Royal Society of Chemistry. The discussions from this meeting were written up in a report that is now available on the NERC website, which you may want to look at. So that's enough from me. It's a great pleasure to welcome Fred and to ask him to give his lecture this evening.
Thank you, Nick. I hope you can all hear me. I was unfortunately fiddling with the radio mic earlier, which meant that I think I managed to turn it off, break it, and link it to next door or something. I'm Fred Worrall. I'm from the Department of Earth Sciences, the University of Durham. I'm an environmental chemist, so maybe I'm the ideal person to be standing this close to the divide between the two societies. But to my shame, and because I'm an egalitarian, I'm actually a member of neither. So Nick has very usefully introduced some of this, so I can move through my sort of background slides relatively quickly, and that is that I think I got this invite because I was one of the 15 UK scientists who went on this meeting in Arlington in the US in last November. But I have to say I am not going to present any findings from that. That is on the NERC website. It's a document you can go and download, so this is not a presentation or a launch of that particular document. And indeed, as Nick told you, I am actually a member of REFINE, Researching Fracking in Europe, though I think it actually now doesn't have an acronym status. I think it's just we collapsed that slightly. Though I'm not speaking on behalf of REFINE, so this will be the only REFINE badged slide you see. But just to say, a lot of the funding that a lot of the research I will be presenting was actually funded by a number of people. So in the past, Shell and Chevron, but also currently GDF Suez, Centrica and INEOS, and the Natural Environment Research Council. And you're more up to date than I am, Nick. You are correct, absolutely correct. The Environment Agency should be on that top slide. The consortium includes currently, it's led by Newcastle University. It was formerly led by Durham, but it does include both Newcastle and Durham, the University of Cambridge, Stanford in the US, Kiel, Strathclyde and Hull. And we indeed have our advisor stakeholders, Environment Agency, the British Geological Survey, DEC, and the JRC of the European Commission. And we have indeed our supporters, the professional bodies, the JOLSOC next door, and the RSC here. So I should just acknowledge that. So that's where my funding comes from, and indeed we work under the mechanisms that Nick introduced. So what is the point of this talk? Well, I think we're all relatively aware of the fact that fracking is a controversial topic. So you can easily find on the web, or you've heard of, anti-fracking movements. You can also, of course, find the pro-fracking movements, and it appears that people easily divide between the two. I'm not going to be here to talk about the truth about fracking, the facts behind fracking, the debunking of fracking, because the moment I do that, everyone in the room will hate me for some reason or other. Yeah, and that's not my object this evening. And when Mindy invited me to give this talk, I thought, oh, look, I looked at all the sort of public lectures and they all had wonderfully wacky and witty titles. And I thought, no, this is fracking. The moment I try and make a pun, I'm going to offend about 50% of the population. So I won't do that, hence my rather straight title. And afterwards I thought, well, maybe we're acting like a referee between these two sides. So maybe I could refer to being a referee. Because a referee, a good referee, as you know, the ideal referee is hated by both sides. Yep. Both sides think he's biased. Well, maybe that's where I should be talking science as the referee in this controversial. Then I thought, no, I'm not a referee either. I'm not that powerful. I don't get to make any decisions like a referee. I just get to provide the science. I'm not a decision maker. I'm not a policy maker. I'm not a regulator. So in the end, I had to stick with a dull title. Yeah? I'm not here to espouse fracking. I'm not here to be anti-fracking. I'm not here to tell you how we'll make those decisions. That's not my job. I am here as an evangelical agnostic. Yeah? I have no opinion on the matter whatsoever that I'm going to give out. So you're thinking, well, what's the point then? And I think this slide sort of illustrates it. Here are two news reports from two excellent journalists who you would know if I named them. In fact, I think the name's actually on one of them if you look very, very carefully. You'll see here are two headlines: debunking UK fracking emissions, and this one, fracking fears raised by methane gas study. Now you're thinking, oh, that's quite common in the media to see these two sorts of headlines, one sort of pro, one sort of anti. The problem is they're both about the same journal article. Oops. And this is sorry, I pressed too hard. And this is the journal article here. It's the same journal article, came out earlier this year, of which I am a co-author. This one journal article generated these two pieces of news. Completely different, apparently, in their headline figures, their headline information. So this is where we sit. Refine and myself, our job is to produce the science. We live in a world in which we're actually going to have, and I'm not blaming these people for doing that, they have a job as well, yeah? But that's the sort of situation we exist in. Producing scientific papers, peer-reviewed, etc., read by our sponsors beforehand, etc., but then interpreted in vastly different ways. So I hope I'm not here this evening to do that interpretation. What I think I'm here this evening is to actually present some science. So, what is the point of this talk? If I'm going to be desperately trying hard not to be controversial, you might want to say, well, it's a sunny evening, perhaps I should hit the pub now. Well, the problem is that, what am I going to talk about? Well, first of all, there is yet no fracking industry in the UK. So if we're interested in the impact of a fracking industry, we could just be sitting twiddling our thumbs. And in fact, Refine started now almost 3 years ago. What have we been doing for the last 2.5 years if we have no fracking to actually measure? Well, how do we understand something that hasn't really happened yet? And so I think that's a really legitimate scientific question. What are we doing as scientists? We make observations, we propose hypotheses, we make further observations. Those hypotheses, of course, are predictions, and we go out and test them. So that's actually, to me, is a really scientific, really fundamental set of scientific questions in a very scientific, strict scientific methodology. So what am I going to look at? I'm going to suggest that there are about 4 things we can do. We can actually learn from the US. Yeah, the US has been having high volume fracking for decades now, or of the order, high intensity, high volume fracking over the last, say, 10 years. We do have a current onshore oil and gas industry that uses well pads, so therefore it's an analogue. It's not exactly the same, we can't say that, but it's an analogue. We have some other analogues coming up, and in fact, Nick has slightly blown my story. Yes, we could look at sewage treatment works, but why we might look at sewage treatment works we'll come to later. And also, we can prepare a baseline. If we want to know something, the impact of something, we need to know what the condition is now, so we have something to measure against to say whether it had an impact. It may not have an impact, but also, by demonstrating if there is an impact, we know what to mitigate, we know what to remove, we know what measures to bring in. So I'm going to touch on some of those. Some I'm going to touch on more than others. So, just to give some context, what about the current UK gas situation? Well, we use about 2.8. These are 2012 figures. They were sort of right in 2014 when I checked the 2014 numbers recently. So it's the sort of general context. The picture to take away is we use around about 2.8 trillion cubic feet, and I'm sorry that the hydrocarbons industry still often work in imperial, not SI. For those in the room, it's about a factor of 35 to get to SI cubic meters. So we'll be working on that. What we have is that that's where our demand is about 2.8. We get most of it more or less, it's getting close to 50-50 between our own indigenous supply from the North Sea and importing it. But the trend is towards more imports, certainly. And so we will be reliant on imports. But most of those imports are coming out of the Norwegian sector of the North Sea. There's a little coming out of Holland, and then there is a little coming across Europe via Belgium. And of course, there's the liquid natural gas in there. What about the scale of any proposed UK shale gas industry? Well, the first question is, what UK shale gas industry? There isn't one at the moment. There is no shale gas being extracted. We actually have around about a median, now geologists worry about these words, estimated median recoverable reserve of 130 trillion cubic feet. There's about 1,300 trillion cubic feet in place, but the recoverable bit is around about 10% of that. Remember that therefore you can do that comparison, 2.8 per year compared to 130 that is thought to be recoverable. I'll come back to these numbers later on as to whether that's actually environmentally possible. In the 14th licensing round last year, 153 license blocks were given for shale gas exploitation. Now that number slightly varies in the talk, depending on exactly the definition of licensing blocks for shale gas. So I just remember that it becomes 159 later in the talk. There is a reason for that, and I just think I was slightly imprecise, so don't question me about that one afterwards. And here's the sort of areas we're talking about. The famous areas, of course, will be in Blackpool, Quadrilla's sites at Priest Hall, etc. And we'll talk also a large amount about the Vale of Pickering in here, and that's where most of the data are from. But I'll also talk about places like the Widmerpool Trough and the Gainsborough Trough further south. But just to compare, if we said we're learning from the US, the scale of the US industry is an order of magnitude larger. In March 2015, the US was getting 40 billion cubic feet of gas a day from shale gas, and relying 55% of its natural gas production was coming from shale gas. The number of wells is phenomenal. In the Eagle Ford in southern Texas, they're going at 2,415 wells in production in 2013. There were only 65 in production in 2009. Yeah? Now, wells does not mean well pads. Yeah? So we'll use those two. You can put multiple wells on one well pad. So that was wells in production, not necessarily 2,000 well pads. Yeah? But equally, the Barnett in mid to north Texas is running at 16,000 producing wells. Yeah? I don't think we're ever going to get to that number in the UK. Oh, there should be a map coming up. Yep. Just to show you where we are, here's the Eagle Ford down here. There's the Barnett. And of course, the big famous one is the Marcellus here, mainly in Pennsylvania, but running all the way through the sort of mid-northeast of the US. So where are we going to start? The first place we can start is we can look at one particular issue the Americans haven't really covered, and that is well failure. Now, what is well failure or well integrity? Oil and gas relies on wells in the ground, and wells in the ground are multiple structures. They're steel casings and concrete liners. They have multiple levels of protection and construction, all of which can fail. And there's about 6 different failure modes here. They can fail during production, and they can fail after production, post-production. So one of the issues here is that if we're about to drill more wells, will we actually have a problem of these wells leaking? Because one of the things we've discovered in Refine is that actually one of the fastest ways of getting contamination is actually because the borehole represents a conduit between deep 2 something 3 kilometres down, and the surface. So if it's going to be difficult to get fluids back up, leaking back from 2 to 3 kilometres down, we've conveniently drilled a pipe between the two, and if that pipe then leaks, we've created a conduit for getting material in the wrong place. A fugitive emission, a water quality issue. So well integrity failure during production or after production becomes a problem for us. So we've been looking into wells and how they're doing. Now the US, we have information on well failure in production. And the numbers reported there are around about 6% of wells in southern Pennsylvania in the Marcellus failed during production in their lifetime of production. About a 6% number. But the Americans are not telling us about what happens after we finish production. Now, the hydrocarbon industry has this unfortunate use of the word abandonment, or abandoned. They don't mean abandoned like we mean abandoned. Yeah? They mean decommissioned. Yeah? So I'm going to endeavour to stress that when the word abandoned is used, it means decommissioned. And when I mean abandoned, in the common sense, everyday use by a scientist community, abandoned, I'll try and make sure I keep those two definitions separate. The oil and gas industry mean, when they say the well has been abandoned, it means the post-production decommissioned life of that well. Now, when they do that, they're talking about the well being actually sealed, cut off, welded shut, filled with concrete and buried, i.e. it is properly decommissioned. Now in the UK, we have 2,150, this is one of my favourite statistics, that's why I memorise it without looking at the screen, 2,152 oil and gas wells in the country, and they're all the little red dots on here. Yep. So you can find one nearest your house. Yep. Yeah, except if you live in Wales. Apparently we didn't do much in Wales. So you can look at those. Now that's a lot, and 65% of those have been decommissioned. Yeah. 143 are active or in some form that could be active in the last decade. So there's about 7% that are actually in that state, which means there's about 27% where we have still some sort of surface structure at the surface but no activity, i.e. they have been abandoned as opposed to decommissioned. Now I was going to actually slightly modify this number this afternoon when I looked at it, and that's this number here, this 53%. 53% of the wells have an interesting ownership history. We can call them orphaned, though strictly speaking we think that only 15% of them are truly orphaned. Orphaned means, in well terms, means they have no known owner. They are truly abandoned in terms of they get left to wander the streets or whatever. No, that's not true. They just don't have a known owner. So somewhere between 53 and 15% have some sort of complex legal ownership, yeah, or orphanage. Yeah. So what we have done, at least we could do initially, was we could look up whether these 143 active wells actually had any reported problems. Now we know that there were, in the last decade of this 143 active in the last decade, there were 9 reported cases of pollution incidents on those well pads. Now that may not have been well failure, and that pollution incident can mean everything from just rang up the Environment Agency to report it and the Environment Agency said, nah, you're all right. Yeah, to a major incident involving emergency services. But that's interesting enough, that number is 6%. So there's a very similar number between the US and the UK in terms of the wells that they have. But nobody went out and measured these, so our job was to go out and measure these things and see whether some of these decommissioned wells were actually leaking or not. So that's what we did. We actually went out and looked at 103 wells, 102 decommissioned ones and one that was not decommissioned, it was truly abandoned. And somebody asked me yesterday, why 102? Well, we aimed for 100 and we did just slightly better. So that's why it's 102. We covered 4 English basins, so the North Yorkshire one, the East Midlands province, and the Wessex and the Weald basins down here. Yeah. We deliberately chose from 4 basins to give us a range of geologies, and we deliberately chose a range of drilling histories. So some that were 10 years old, some that were 80 years old. Now, the word used is spudding, is the date of drilling. We don't know consistently the date of decommissioning, so we couldn't do it relative to the date of decommissioning. And then we wanted to model how much material was coming out of these, if there was indeed any material coming out of these. Oh, sorry, again, jumped ahead slightly. Is that going to go back? Yeah. So this is what decommissioned wells look like. These are 2 we didn't actually measure, but you can see here, there's the well pad, Yeah, that'll have been the site of the well. They planted a tree on it. And here's one here. There you can see these have been properly decommissioned as far as we can tell. The well sits more or less in the middle. There's the square. They have been decommissioned back to something. Yeah. You do get complex ones. This is the Formby site. We didn't study the Formby site because half the time we wouldn't know which well we were over. This is the well field. It has been properly decommissioned. It's been returned to arable land in this case. But you can see how many different wells there were actually in that well, on that well site. And so therefore we didn't study that one because it would have been too complex to work out which one we were over at any one time. How do we actually do this? Well, one of the things I want to stress about this, as I said, you know, the role here is as scientists. And I want to stress that one of the things we're very careful about is how we do our surveys and how we do our experimental design. And I'm very keen that one of the things that when I came into the fracking research area was I noticed the poor statistical design of how studies were done. So you'll hear me emphasize again and again that one of the things we always have is a control. It seemed to me obvious as a scientist we have a control. But it was interesting how much the literature was missing that. So what we're interested in here is we're going to measure this well here to see if it leaks. There's the well in the middle there. We're going to measure various locations running a transect across the well. And you're going, why do we need to run a transect when that's the well? Well, first of all, it's not always possible to know exactly where the well was. Yeah, so that partly allows us some uncertainty in where the well was. It also means that we've got no evidence to believe the well is actually leaking vertically. It could be leaking slightly that way. Yeah, so it gives us a measure of actually those possibilities. But the important thing here is also we always went and measured a control field. And the control field was the closest possible field with the same land use. Now, most of the time, that's a grass field next door. Yeah? So we always measure control. So all of my results are relative to a control. So our ideal hypothesis is, if there's a leak, we will actually see a number greater than 1 because it's judged relative to the control. We also made sure that we always adjusted for the weather on the day. If you're measuring methane coming out of the ground, things like atmospheric pressure make a difference. Or at least they're supposed to make a difference. So we were measuring atmospheric pressure, humidity, temperature, all those sorts of things on every day. And we're measuring soil gas, and this is Sam out. I noticed that all my slides, when I have any of my research group in, have all got the right personal protective gear on. So I'm really impressed by that. In fact, excessively so in one slide in a moment. So let's start showing some results. All my results, therefore, are expressed relative numbers. Yeah, here. So again, we're expressing relative to the control the whole time. These are the different basins, the Weald, North Yorkshire, East Midlands and Wessex. And I try to, again, because we've designed this as we have, we can express them as the mean and the 95% confidence interval. So we can judge something as being significantly different from the control. In this case, it looks like the Weald geology would tend to actually give us higher numbers, whereas the Wessex geology would tend to give us lower numbers. You might begin to think, ooh, that's significantly lower than 1, i.e. not only is it not leaking, it appears to be doing less than the control. We'll come to that in a moment. What about results by well? Well, I've listed them from the highest recorded number to the lowest, all 102. I could have put the 103rd on, the non-decommissioned well, but it would have so distorted the graph, it plots at 35. So it would have been well off the axis here and would have spoilt my nice, pretty sort of sigmoidal pattern. What we have here is, again, everything's plotted relative to 1. These are 95% confidence intervals. Yeah. So what we can see is a large number of wells. We would say there's no leak whatsoever. We would also say there's a fair number of wells in which we're actually not only not leaking, we're actually below the control, but also we do have a number up here where we are judging significant contribution potentially compared to the control. Which bit's working? That bit. What about the age of the well? So we deliberately chose a range of ages and we put them into 10 decadal bins at the bottom here, number of wells, and also the proportion that did not leak. I know that sounds odd, but it's the proportion that didn't leak. Now, you can look at the statistics of this. That is no significant difference across there. Now, that surprised me because I thought the oldest ones would be more likely to leak proportionally. But what it appears to be here is that actually, if a failure is occurring, it's occurring soon after decommissioning. And it appears the well site comes to some sort of settled position, which then doesn't change. That settled position could be a slight leak, or it could be no leak whatsoever. But it doesn't appear to shift particularly over time. So what have we learned about well integrity here? Well, first of all, these two slides are not decommissioned wells. This one here is Hardstaff 1, the earliest well we have still extant in Britain, and this was the non-decommissioned one we went and visited. Hopefully you worked out that's not decommissioned, that's not been welded shut, sealed with concrete or buried. Yeah, that is actually perfectly visible in the plant nursery in the village of Hardstaff, and the plant nursery owner is always keen to show it to people. In fact, it sits bubbling at the surface. He's quite, and in fact the village has on its welcome to the village sign says home of the oil and gas industry as its tagline. So it's very, very proud of this well. The one up above is a CBM well, coal bed methane well, in Sunderland. You can see that one wasn't decommissioned either. It has now been decommissioned because it's sitting under somebody's house. That's a building site. Don't worry about that, it's not a particular problem. It's just an example of that some of these things are not decommissioned. So 30% of wells we were seeing statistical leaks, but 39% we weren't. Yeah, that were actually lower. Now we're ascribing that to the action of the buried well pad. This is a concrete well pad under the soil, it's under there. It's potentially restricting some of the normal soil operation. So we've got an avoided loss there as well to think about. An integrity failure occurred soon after decommissioning. Yeah, well, that's what we're suggesting. What about the flux? Because what we want is some sort of emissions factor that we can go away and put into regulators' numbers. Well, we calculate that. It's a simple diffusion problem. We've got a known source at a known depth. Well, sorry, we've got an unknown source, but at a known depth, and we've measured effectively a plane above it at a known distance. So therefore, we can just actually calculate that. It's fixed law. We can simply do that and get numbers out. And there they are, 300 and something, plus or minus 600 kilograms CO2 per equivalent per year. Note that that allows us to have the avoided loss. So some of those numbers are below negative, some are positive. The 95th percentile, because we've got to be cautious, is this one here, 296 kilogram CO2 equivalent per well per year. That means that we can, we can compare that. Now, is that big? Well, first of all, the non-decommissioned well, Hardstaff 1, was running at 8 tons CO2 equivalent per year. Yeah. So the first thing we can learn is that decommissioning seems to be quite a good thing. Yeah. If you're going to have a well, please decommission it. The other thing we've got to see is this number 296, is this big? Well, I like to compare it to sheep. And I'll do that later on as well. Emissions factor for one breeding ewe in the UK is 205 kilograms CO2 equivalent per head per year. So our 95th percentile well is leaking at an equivalent rate of 1.5 sheep. Yeah. Now, I like to put this picture up. Here is a field of grass somewhere in southern England. So this could be a decommissioned well pad. Yeah, that's often what they look like. So this decommissioned well pad, 1 to 2 hectares. In 1 to 2 hectares of land in southern England, you can run between 20 and 40 sheep. By the time you've put the third sheep on there, you'll be producing more methane from the sheep than the leaking well. Yeah. So it's an interesting contrast. What we're saying here is we've explored an issue, we've come up with the fact that there are some leaks, we've tried to statistically prove them, we can do that. We've come up with an emissions factor. The emissions factor is relatively small, and the activity level is relatively tiny. There are 2,152 possible decommissioned wells in the UK. There are 32 million sheep in the UK. I checked that number this afternoon. Yeah. And you're going, well, what about other emissions? What are you exploring? Well, again, we've got the same principle here. We can keep going like this. What about emissions from faults? People, and if you explore the geological literature, there is quite a row going on at the moment about whether faults will be a problem in fracking. What do we mean by faults here? These are the basin bounding faults. So this is the Widmer Pool Trough, Nottinghamshire, Derbyshire, sort of Leicestershire area. Here's the big block of shale that they want to actually frack into. Here's a basin bounding fault. If that basin bounding fault is a conduit of gas, you could be fracking in this area here and lose all your gas to the atmosphere because that fault is operational. So there's a big debate at the moment as to whether that's true or not. Here's the Gainsborough Trough. Here's that target shale. Here's that basin bounding fault. So we said, well, let's actually see if we can detect methane coming up those faults. So again, we design our experiment with controls, with multiple replicates. We chose 5 basins. Yeah? We chose 2 shale gas basins, the Widmer Pool Trough and Lancashire. We chose 2 coal basins. I happen to live in a coal basin, so that was relatively easy. We chose the north bounding fault of the Durham coalfield and the south bounding fault of the Durham coalfield. Why coal basins? Because of methane, they should, of course, be potentially leaking methane out. So they were sort of potential good comparators or good targets. And one non-hydrocarbon basin, which is the Pennine Fault in the Vale of Eden here. Yeah. So again, a deep-bounding half-graben fault that's got an equivalent depth, but of no known hydrocarbon reserve in the basin. Yeah. Now, scientifically, how are we going to do that? We're going to measure real-time. I keep pressing the wrong button. Go back. Yep, sorry, we're going to measure the real-time methane concentration, but we're also going to measure the isotopic composition. We're going to use a cavity ring-down spectrometer. I'll show you that in a moment. We're going to measure basin-bounding faults and controls on the same day, and we're going to actually do an awful lot of effort to correct our data, and I'll tell you some of that later. Let's just show you the equipment. I sort of feel safe doing this in a chemistry audience somehow. Again, look at the personal protective gear here of Ian, my postdoc. High-vis jacket and a hard hat, and he's only in the car park. So that's very, very good. The cavity ring-down device is in the back here. This is just the laptop processing the data in real time. We also have other data loggers for wind speed and things like that. The device is here. There's the anemometer on top. It goes into a pipe with the spectrometer sat in the back of the car. Yeah. We get a lot of people waving at us simply because they think we're the Google Earth Street View car. Waving being the kind term for it. So we can record concentration at a 1 Hertz type signal and the isotopic signature at a 1 Hertz, so once a second. Yeah. What does that mean in data terms? Now, the usefulness thing about methane isotopes is that methane isotopes in the atmosphere, the 13C stable isotope signal is about -50, and it's pretty good. That's pretty stable. And it has a concentration about 1.5 ppm. And that is, on these sorts of diagrams, about there. Yeah? So this is 1 over the methane concentration against the isotopic, the del 13 signal. So atmosphere will be in about there. Yeah? Now, if we detect something that's thermogenic or geogenic, it tends to be isotopically heavy relative to that. So we'll be looking at a concentrated source that's isotopically distinct. If it's biogenic, it will be a concentrated source that's isotopically light relative to the atmosphere. So in this case, here's the low concentration source with an atmospheric signal. Here's the high concentration source, isotopically lighter, so this is biogenic. Here's one where we've got the atmosphere at this end again. The low concentration source has an atmospheric signal. The high concentration end has a geogenic or thermogenic signal. So we've got two different gradients that appear on this graph. Now, it's not always true, but you're into the 99% of the time that is true, that's actually a good indicator. It splits pretty clearly. Now, to get these numbers, what we do is we have to sit around for about 10 minutes to get this sort of graph. Yeah? Because the wind is coming in and it's making a sort of admixture of those two sources. And so therefore, these are a mixing line type plot that we can use. Here's other examples. These are some of the best ones we've ever seen, I will say, because they're not like clear straight lines. They normally look like this. Lots of atmospheric data and the occasional stray one that tells us whether we're looking at a thermogenic or a biogenic source. So this one's biogenic, this one's thermogenic. Now, this is what our data then looks like. We can drive around. We can drive up to 50 miles an hour with this device because it will correct for our signal. It's because of the GPS on it. Now, what we see here is the purplish area is our wind field area. So that's what we're taking signal from. We detect anything above ambient. Yeah, and so we get what we call a ping. And we can therefore detect also the sort of area that the wind is pulling that methane from. Now, this is actually just on the outskirts of Newcastle. The 90 fathom fault comes in and across here and out the other side. And this is what we thought was brilliant. Excellent. We've detected the fault line. You know, there's methane coming up this fault on the edge of Newcastle. It's nothing to do with the fault whatsoever. Yeah. Went back, of course, and now we measure the isotopes. Every one of these is biogenic. There's no thermogenic signal here whatsoever. The sewage pipeline comes in along there, crosses the bridge and out. Yeah, we managed to detect Northumbrian Water's network. So did we manage to detect anything on this process? Well, this is now, again, the 90 fathom fault. So this is now Corbridge. This is the one we call the Corbridge burp. Corbridge is just to the north, the Tyne is just to the north. Now I'll show you this first of all signal. So we've got a cluster of pings coming in here, and I've included this one here. Yep, so detection. Now, if I tell you that all of those are thermogenic, you might go, but it doesn't necessarily have to be the fault, does it? It could have been a high-pressure gas pipeline or something like that. Now let me show you the map with the fault line drawn across it. The fault line comes through here, out here, and we're sat there on the projected line of the fault. The interesting thing is that little ping there was biogenic. So what we've got here is that we've got elevated sources, thermogenic on the fault line. So we've got 3 tests. But we can do better than that. Here is the data we sort of run. This is now where our experimental design comes in and our survey design comes in, because it's not just those 3 criteria. We can do this statistically. We can run the fault line. So this is the North Pennine or the East Pennine bounding fault here. Carlisle is just up here. Yep. This is the East Pennine bounding fault. So what we do on any one day is we get the car and you can't run the car along the fault line. Yep, farmers don't like that, nor does the car. What you can do is you run the road network backwards and forwards in the area of the fault. And you can run a control line. Now what you in fact do is you run a ghost line, or a ghost fault as we now call it. We actually draw a fault across the map and go, let's make a dummy fault. And then we drive around the dummy fault. So our control is we take a piece of country where there is no fault that looks like the country where there is a fault, and then we treat it as if it is one. So that's our control. So what we've got here is our control fault line is down here, and there's the real one. We also then drove a second fault over here because it was nearby. So we survey a control line on every day when we're surveying a target line as well. And we've got to effectively say that those 2 are different statistically. Now, of course, we actually have to throw away a lot of our data, because what happens if the wind was coming the wrong way across these faults? So we have to adjust for the wind. We have to adjust for the wind speed, the wind direction, and the distance to the fault. Yeah. So what we do is it's a Gaussian plume problem. Yeah. So what we have is a source that we believe is constant, and it's diffusing away from that source in 3 dimensions. At some point in space, we are sat monitoring it. Yeah. So we know the height of our monitor. We assume that the fault is at ground level. And we can effectively say, if we know the distance is there and the distance there, we can project those 2 distances. We can correct for our distance. It also means that if that is not true, i.e. the vector of the wind is in the wrong direction, we throw away the data. Yeah? If the wind isn't coming over the fault, it would be unfair to actually claim any concentration in that sense. It also, of course, we've got the additional test on the top that we're wanting to detect geogenic material. Yeah? So does this work? Again, we can do now the statistical plot. So we can compare for each basin, whether it's the 90 fathom, which is a Durham coal basin, the Butterknoll is a Durham coal basin, Widmere Pool is the shale gas basin, Lancashire shale gas basin, the Vale of Eden. So we can do this statistically by basin, etc. What do we do? Yes, we do find that faults are significantly different from their control. But here's the caveat on that. Yeah? Look at our big differences are in the 90 fathom, which is a coal basin fault, and the Vale of Eden, which is a non-hydrocarbon basin fault. So what we're saying here is, yes, faults can be a conduit, but there's nothing special about shale gas basin faults. They may or may not be conduits. Faults can be, but there's nothing unique about shale gas basin faults. Now, I showed this slide yesterday at a talk to petroleum engineers, and you could see all of their eyes lit up, because what they were going is, no known hydrocarbon. It's probably because it's acting as a groundwater conduit. It's bringing deep groundwater up, and that's actually contributing to methane. Yeah. What about infrastructure? When shale gas first came into the problem of fugitive emissions and the greenhouse gas impact of shale gas first came to the fore, some guys from the US, led by a chap called Howarth, published a paper. That paper was universally vilified and attacked. It's actually a very, very honest paper, and it's really worth a read, because the guy has to say, we don't have a lot of data, but given the fact we have virtually no data, what is the greenhouse gas impact of a shale gas industry going to be? And he's very, very honest, and I think that was his problem, because he actually admitted that he had no choice but, for example, use 1970s Russian data for pipeline emissions. In the footnote in the paper, if you read the paper carefully, he actually admits that some of his data had to come from a PowerPoint presentation he took from a colleague at the US Geological Survey. And that's literally its source, PowerPoint presentation, US colleague. And he's perfectly honest. But what he got effectively criticised for was no data. And the answer was, well, it wasn't because he had deliberately avoided any data, it was because there was no data. So one of the tasks of Refine, therefore, is to fill some of those gaps. And it's something we can do just as well as a shale gas industry in America. We can start filling in those gaps in a UK context. So what we're doing here is we're measuring pipelines, and these are all high-pressure gas mains. Yeah. Will pipelines leak? Well, the advantage is, of course, a pipeline is another good target for us, like a fault. It will be a high concentration, thermogenic, geogenic source, so it will be quite isotopically distinct from a biogenic source. We surveyed 5 pipelines of varying age. Every day we put a control in as well. So it's almost exactly like analysing a fault. So this is an example from the Vale of Pickering. Indeed, doesn't come up too well, but Pickering's in here. Moulton is down here. Here's our, unfortunately, Ian chose green for everything. There's the high pressure gas main. That's a part of the national grid of high pressure gas mains. And there's our survey line going backwards and forwards across the high pressure gas main. We do the same thing. We effectively draw a ghost gas main through countryside that has no high pressure gas main, and then we survey backwards and forwards. And you're going, yeah, Fred, why didn't you just draw it a little straighter? Well, there's a gas field actually in here. There's a conventional gas field, which I'll show you data for. So we were having to avoid a conventional gas field so that we didn't pick up a problem. We also deliberately went through Moulton because this pipeline deliberately goes through Pickering. So we did go through an urban area. We were selecting it. And as you can see here, we get plenty of pings, the little red dots along the pipeline, but we do get pings along the control as well, because there are low pressure gas mains, there are landfills, there are dairy farms, all those sources are there. What we always have to demonstrate all the time is that the material coming from the pipeline is statistically different from the actual amount that we would detect in the countryside of similar type anyway. So again, that's that statistical exercise we've got to put ourselves to and be rigorous about. Well, can we detect them from pipelines? The answer is yes, and I'm sure you're not too surprised about that. And that's not what I'm going to try and emphasise here. I'm trying to emphasise here the opportunity this sort of detection gives us. So we can actually detect 88 leaks per kilometre of pipeline. And you go, 88 leaks per kilometre of pipeline? I was horrified at that. And then I remembered that 1,000 metres divided by 88 is 1 every 12 metres. How long's a pipe section? It's 12 metres. Yeah. So what we've got here is that we're actually measuring almost every joint in that pipeline. Now you're going, is that a good thing, bad thing? Surely pipes don't leak. I mean, if they were leaking, high pressure gas main, it would be jumping out of fields all over North Yorkshire and whatever. No, think about the scale of these things. The hole required, we again spent a lot of time looking on things like detection limit. Within the equipment that we use, the hole required to trigger something above our detection limit would be the size of a computer pixel. Yeah? 0.05 millimeters squared. It's actually slightly, I was disappointed by this, it's slightly larger than the diameter of your human hair, because everyone compares things to, swimming pools, human hair is the size of whales. I had to go and find a different comparator from one everyone else uses, because it's slightly larger than the diameter of your human hair. The advantage here is now what have we managed to show? So first of all, we've shown that we've actually got a very small leak, but it's got a high activity level, i.e. it's almost every joint, in a high pressure gas main network where there's 7,000 kilometres or whatever of high pressure gas main network in the country. 7,000, 2,000. It's a lot. Now the opportunity here is not, there's, do we dig up every joint? No, of course not, because the moment we started digging up and replacing any joints, we'd still end up with this number. The opportunity here is to actually think about that this is an inherent property of those joints. This is the microporosity or nanoporosity of those joints. This is the diffusion constant of those joints. But let's look at different types of joints and see which one has the lowest. So we can guide best practice here. We can potentially then say, well, this is our mitigation strategy. And the potential power of this mitigation strategy is because it's on every joint. The activity level is very, very high. So one of the problems when we were talking about leaks from wells is that there's only 2,000 of them. A small leak from 2,000 wells doesn't scale very well. Small leak from length of pipeline scales an awful lot better in terms of mitigation strategy. So what we're looking at here is, can we actually, this then allows us to pick and choose our engineering joints. Not that we're going to say which ones leak and which ones don't. We're going to say which ones effectively have a lower intrinsic leak or porosity, or D. This could be the diffusion coefficient of those leaks. But our techniques are sufficiently sensitive in the field to pick these things up. What about next steps in doing this sort of thing? Well, there's a whole infrastructure network out there to actually look at that's already in place that we will be using more of if we have a shale gas industry. This is a transfer station. So a high pressure gas main comes in here and leaves through the medium or lower pressure network. And we happened to be driving past this, and of course the machine went crazy. Yeah, instantly detected it. And we've now actually got permission to go and sit the car outside 2 of these to actually start doing again, studying what's the emissions factor for these sorts of activities. And the company's very keen on this actually, because what we're showing them is we're not actually showing that they're leaking or polluting, we're actually looking at their performance as a different measure. Yeah. We're giving them the opportunity to actually find mitigation strategies. What about an onshore conventional field? We have onshore conventional fields. These are our best and closest analogue to a shale gas industry. So for example, here again is North Yorkshire, there's Moulton, there's Pickering, this is the Kirby-Misperton field. And Kirby-Misperton has a real advantage that it's virtually a closed system. It's not quite a closed loop system. There's a well pad here, a pipeline. No, so just before you think that's where the pipeline actually goes, I didn't map the pipeline all the way across it. I've drawn a schematic pipeline. To the East Knapton power plant. Yep. So we can put in a control site, we can put our kit on the well pad here, and we can put our kit on the power plant and on the pipeline. We've got the whole network in a distance of 5 kilometres. And so indeed, that's what we're actually doing at the moment. The guys are physically, well, they're not, because it's this time of night on a Friday, I suspect they're not there now, but that's where they've been today. We've been looking at well pads, generating station and pipeline compared to the rural control. And this is quite a nice contrast, actually, quite nice politically. This is Third Energy's site at Kirby-Misperton. There you go. Again, look at this the personal protective gear, all in place. Measuring the emissions from this well pad. And here, in fact, is the control site. That control site is owned by the Secretary of Frack-Free Rydale. So we do feel like we're travelling in no man's land between the 2 ends of the spectrum here. But that's what we're doing at the moment. So again, it's the same principle. Let's actually keep our controls in place. Let's do it statistically. Let's get our emissions factors right. What about other analogues? Nick mentioned it. What other analogues do we have? Well, one of the other analogues we have for a modern well pad is a sewage treatment works. Why? Well, a sewage treatment works like this is a zero discharge well pad. In here is a zero discharge well pad. This is, I'm allowed to tell you where this is. You'll spot it. It's Shap. It's the village of Shap's water treatment works, sewage treatment works, sorry. And that is about the size of a well pad for shale gas. It is a zero discharge well pad, but also, of course, remember that it has lots of incoming chemical and it has lots of potential pollutants on it, but it's designed, as in word, the best available technology for American well pads. So we have an example here of something that's operating in a rural setting with large amounts of potential pollution, and it's operating on our best available technology that we would potentially use on well pads. So we can look at the pollution incidence or the performances of these and say, well, do what we call a zero discharge well pad actually become a zero discharge well pad? Yeah, got it. What about drawing baselines? What about learning from things that we've actually already doing? Well, again, the way to do this is potentially look at biocides. There are 13 organic biocides currently used in the US in fracking fluids. Bizarrely, none of them are used in the UK whatsoever at the moment. The other thing I should note is that the UK will probably have a lower demand for biocides in its fracking fluids because of the way we will run our industry and the way we'll use our water resources. But we actually want to know, therefore, what's the potential threat. So we have an interesting problem here. We measure biocides all over the place in England. Here's the map of biocides detections in the last decade in England. But they're the wrong biocides. Yeah, they're not the biocides that were going to be used in fracking. So can we learn from what we have observed to what might happen? So we examined all English groundwater sampling over the last decade. That's 1,475,000 observations. Yeah. We know where they are detected. Yeah. We know the areas and amounts of the compound applied. And then we can effectively model towards the ones that might be used. Oops, that way. First of all, we can do things. First of all, let me explain that biocides are very, very infrequently detected in UK groundwater, and this is a confidence builder to start with. Out of the 1,475,000 observations, there were only 2,234 detects, so an incredibly small percentage of detection. The interesting thing, though, is of the 110 compounds actually looked for, 95 were detected. So in general, if it's out there being used, it will eventually get detected, even if in tiny quantities. That's an observation. First of all, then we could look at solubilities. This doesn't come out well. The blues are actually all the compounds found in English groundwater and their solubility potted in order. The reds are the 13 that are currently used in the US. They're all at that end of the solubility spectrum. So that might give us a bit of a warning. But solubility doesn't necessarily mean contamination risk, because what about degradability? Other things. We should be surprised that things we're going to put down in water are highly soluble. After all, we're going to be mobilizing it in water. So that's not the best indicator. What we're doing instead, now this is a slide I can put up in a chemical audience. I couldn't do this over next door in geology. No, they wouldn't understand it. Here you go, here's our nice chemicals at last. We're going to model, what we're going to do is we say of those 110 that were looked for, the 95 that were detected, the 2,200 and something observations of the 1 point something million, yeah. What we're going to look at is we're going to model their molecular descriptors. What is it about each molecule that means we detect it in what frequency and where? Such that we can do the same for the compounds that are proposed to be used, and therefore we can actually make that comparison. What do I mean by molecular descriptors here? Again, as I said, I'm in a chemical-friendly audience. Things like polarizability, highest occupied molecular orbital, lowest unoccupied molecular orbital, all those sorts of parameters that we can derive sort of from first principles by good molecular modeling software. We're not reliant on things like soil measurements, degradation measurements, things that are dependent on site-by-site conditions. So that's what we're doing. We're going to predict the occurrence of fracking fluids by molecular modelling of those compounds we already are out there in the environment. We're also going to go one step further. We know where those current compounds were detected and where they weren't. So we can use that information to say, well, actually, this area here had a higher rate of detection than we would expect. So potentially the area is vulnerable. Is that an area where we might be actually having fracking activity? So a vulnerability assessment for something like the Vale of Pickering or the Fylde Coast. What about assessing carrying capacity? Now, this is something the US does not have a problem with. If you're in southern Texas, you've got plenty of space. Why is the Eagle Ford such a boom area? Because there's nothing else there. You've got lots of space in which to do it. We don't have that lots of space. So when I said earlier that we've got a certain amount of reserve, 130 trillion cubic feet, yeah, do we really have that amount of carrying capacity to access that? So, for example, the Institute of Directors said that we'll have 100 wells at 10 wells per year. That's how we'll develop an industry. Yeah. Well, the strange thing about that is, and in fact, we ourselves in a paper said we'd have 25 wells over a 10-year period in Lancashire alone. So, well, where did those numbers come from? Well, I must admit, ours were made up. We just said what it was about 25. Yeah. Well, let's have a think about from the resource perspective. From a resource perspective, we have 159 licenses. Okay, it's actually 153 for shale gas, in blocks of up to 100 square kilometres each. Yeah, 130 trillion cubic feet of recoverable reserve. Each well could be actually produce 126 billion. So 130 trillion, 126 billion, that's about 1,000 wells, isn't it? Not 100, as those sort of numbers. Each well can accesses, spelling mistake, 2.5 square kilometres of shale, laterally. So therefore, we've got a 100 square kilometre block that you can start doing the sums. What it says, if we're to access that reserve, we probably need something like 1,000 or more well pads, potentially, and that's at their most efficient. We're only projecting about 100 up here. Well, the question is, where does this meet? And can we as environmental scientists actually see something different? Well, what we've been doing as part of a European project is we've been saying, well, what's the footprint? Now, you can have a direct footprint. This is a direct footprint of a modern, current, conventional pad. Yeah, there we can measure the footprint. But equally, within the environment, we can say, well, what's the offset and the setback from that? Well, the Americans have told us what those should be. They should be 150 metres for wells and streams, and 600 should be the maximum setback. So we can start plonking well pads into those licensed areas and say, well, actually, how many can we put in those licensed areas? You know, is it 2? Is it 3? Yeah. And we've been doing that. We've been effectively randomly putting, now I removed all names because I had a horror that somebody from Nottinghamshire or somewhere would be in the audience and suddenly think we were proposing a well pad on top of their bungalow. we're not. We randomly plonk these well pads and their setbacks into those licence blocks and say, well, if we put one there, what does it actually overlap with? So, for example, here, there's a road, lots of houses. Well, is that going to be possible? So we randomly do this and see how many wells can we put into a licence block if these setbacks are there. And that gives us a measure of carrying capacity. That's a different way of doing it than saying this is the irrecoverable reserve, this is how much we're going to extract. We're saying how much can we actually cope with on the surface. So what, as we come to the end, what have we done? Well, I hope that I've given some example of how we're exploring as scientists the potential impacts of something that hasn't happened yet. We're trying to learn from the US. We're trying to look at the current onshore industry. We're trying to look at analogue industries such as the water industry, and we're trying to prepare baselines. I actually think in that sense we've got a real advantage here if there is going to be a shale gas industry. Yeah. We're endeavouring to use the best science we can to provide information to other people. As I said, we're not the referee, we're not the decision maker, we're not the policy maker, we're not the regulator. In the end, I think the best thing I can qualify to be is a member of the general public. So we're none of those. I think I've got two pictures to end on. The first one is this one. This is Witch Farm. It's the largest onshore oil field we have in the UK. Now, it's on the Isle of Purbeck. There's Poole Harbour. Yep. And I always like to point out that it's actually less than 2 miles from the most expensive housing in the country at Sandbanks. Yeah, perfectly well operating field. In fact, it's also one that's had a pollution incident on it. It's in the pollution incident database. Yeah. The other thing I want to point out with the end, I promised Mindy there would be no jokes because it's not a subject in which we can do jokes. But I would like to point out that fracking has had a very, very long history. And the earliest known example of fracking is this guy, Moses in the desert, providing water to the people of Israel. Thank you.
Fantastic. Thank you very much, Fred. That was a real tour de force, tour through some of the science that you and your colleagues are doing, and some fantastic illustrations there of the sort of real research to go on to actually start to quantify some of these potential impacts. So there are a couple of roving microphones. We've got a little bit of time for questions. Who has a question for Fred? There's a question down the side here. If you just wait for the microphone to reach you so it can get picked up for the recording, that would be great.
Thank you. The question is, you mentioned the analogue of the sewage treatment works. You didn't indicate whether it was zero emission, whether that was the case. The other thing is you're restricting yourself to sort of the just the fracking side and analogues, but there would be some useful information in what the actual range across the country was for other things. So in cities, is it much larger, those rates, for example? What are we prepared to accept for our everyday life in other areas that may not be so motor?
Yeah, I absolutely agree. And the fascinating thing, first of all, let me deal with the sewage treatment works. Sewage treatment works has another advantage, which of course is it's licensed by the Environment Agency. It has a licensed discharge to the local stream. Yeah, it's under the Urban Wastewater Treatment Directive. So in that sense, it has an analogue of regulatory framework that is a really nice one to sit in. In fact, that one, it actually runs into a protected phosphorus stream. So in fact, that's the biggest issue on that particular one. So is it zero discharge? Well, it's zero discharge from leaks because of the way the sump works, and it's a relatively modern one, so nothing has actually happened as yet. But it provides an interesting example of here's a well-regulated industry which we know about, which we live with, which has some of the technology already in place that people are purporting to use. And one of the great things about, to answer the sort of second one as I understood it, one of the great things about coming into, and one of the great things about the fracking world in terms of things like fugitive emissions and greenhouse gas emissions, has it sort of opened an interesting can of worms. As Howarth in his paper actually pointed out, was the lack of data about all sorts of things. So people were criticising shale gas, and then people were going, yeah, but we don't know about pipelines in general. Oh yeah, better go and measure pipelines. And then you get, wait a minute, we actually turned out we didn't know what landfill was doing, and we didn't know what cows were. Yeah, it sort of meant that we've actually had a whole boom in getting our emissions factor better for everything in terms of comparisons. You know, there are lots of targets I would like to go and measure, because the more comparisons we do, the better off we'll know that context. I like sheep because it's something I work on the rest of the time. And sheep tend to have a very large greenhouse gas footprint. So that's why I do, you know. Somebody asked me yesterday, why couldn't I do it in terms of coal mines? And the answer is, I don't particularly like coal mines. I much prefer to work, you know, I compare to sheep. So yeah, I utterly agree. And in that sense, it's an iterative way of improving our models for everything. And it so happens it's been triggered by this industry, or the potential for this industry.
Okay, there's a question just by the aisle here. Thank you.
I was wondering why there's such a punt over the methane gas emissions, when I understand that the vast majority of methane is from animals, from cows, sheep, whatever. Why is this such an important factor that people are so concerned about?
Absolutely is the answer. The moment you compare, I've done these sorts of things, as I said, I work on agricultural impacts a lot, and the moment you work for an estate or whatever, or a large landholder, the first advice you can make to them is shoot the sheep. And you'll make your target. So I remember one particular case where I was brought into a large land holding organisation that you would recognise the name of, and I was brought in because they thought they could manage their peatlands to prevent the methane emissions and CO2 emissions. And to be honest, it came down to how much diesel were their tractors using and how many sheep they ran on the ground. And that's what it came down to. It didn't matter what they were going to do on the peat. They could dig it up and burn it. I mean, it wouldn't have made that much difference. So the answer is, but then that comes into this grey area of what is publicly understood, acceptable, reception, etc. You know, we know there are cows in the fields, we like those. Yeah, this shale gas industry is an unknown. You know, there's those sorts of differences. And indeed, in the northeast of England, you know, every time we go past a mine pumping station, and there are 9 of them in County Durham, our machine goes crazy. Why? Because it's bringing water up 150 metres from a methane-bearing strata and pumping it into the atmosphere. Yeah, the machine goes absolutely wild. So there are all those interesting comparisons, and that's where we merge into what is this perception issue. I think also the interesting thing to think about is, are people so worried about methane compared to other things? So I like to make the analogy is that I've never known anybody, I mean, I work on methane a lot, a couple of days a week I'm worrying about methane, it's my job, but I've never known anyone else walk out of a building in the morning and go, 3 ppm methane this morning, that's got to be a concern. You know, those are sorts of some of the numbers we're dealing with. Is it 1.5 or is it 3? And these are ppm. So in terms of public concern, they can see greenhouse gas and an industry they don't understand, but they're not really working that back to what sort of levels we're talking about.
Okay, another question?
I've got one if nobody else has one.
Peter, let's get the microphone to you.
I don't think this is working, is it?
I think
Oh,
so.
it is.
Hello? Oh, yes. I have one question for you, and that is, in the United States, a landowner who has fracking underneath his property gets a monthly paycheck from the fracking company. Unfortunately, in this country, we had William the Conqueror, and when he arrived, he said the whole of the subsurface in the UK belonged to the Crown, it belonged to him. So as landowners, none of us get any financial benefit from the fact we have a fracking line underneath our property.
Yep.
Would you care to comment on that? Do you think it's going to have a long-term impact?
Well, yeah, that's my understanding as well. One of the reasons why you can get, you know, every farmer in southern Pennsylvania is quite happy to have a pad on their ground is they get the money from it, whereas every landowner in Gainsborough is not going to get a penny from it in that sense. That money will go to George Osborne or whoever comes after him. It's a different, we've lived with that through mining rights, etc. So I think it's an interesting one that means that we don't have that push from the landowners. or the homeowners. You've got to remember, though, if you think about sort of land ownership, we're that much more crowded than an island. You imagine if you actually, the well fields that currently exist in, say, someone like Gainsborough, they actually will go out under people's houses, etc. So you imagine the complexity of working out who you should be paying who if you've suddenly your fracked area contacts some part of someone like Gainsborough or some other village, you know, Malton, Pickering, Kirby Misberton, you know, these sorts of villages that have got gas fields under. So in some senses it brings us an advantage in a relatively crowded island. But certainly it was a push factor, you know, in parts of southern Pennsylvania where farmers were going, great, you know, this can actually... but equally, you know, having a well pad on every farm in southern Pennsylvania, that's some of the issues why, for example, water quality issues came back, because all those small farms all had their own private wells. We don't have that situation in the UK. So centralisation will bring other advantages and disadvantages depending on which side you're on. We have a more complex land ownership structure that would have meant it would be difficult to work out who should be gaining the mineral rights. Equally, because we have more crowded countryside, we don't have the problem of private wells that the US has. Those sorts of, so there is sort of swings and roundabouts in there as to whether it, yeah, but it certainly was a push factor or pull factor, depending on how you look at it, in places like Pennsylvania.
And question again on the aisle there, if you just wait for the mic coming up behind you.
I had understood that one of the problems and concerns with fracking was contamination of the groundwater. Now you've touched on that talking about biocides, but actually that some of the materials pumped down the fracking fluids, whatever they are, could actually get into the water system. I thought that was one of the big issues. I wasn't aware of this methane issue until your talk.
Yes, and it's also one of the reasons why we're so interested in well integrity. The reason being is if you imagine, you've got to imagine a pathway back from depth. So you're going to pump fluid 3 kilometres underneath Yorkshire. Yeah, you've got to get that fluid back up if it's going to be a contamination problem. So your aquifers are shallow, they're 50 metres down, not 3 kilometres down. So therefore, you could say, well, the initial concern was that the fracks would travel large distances and that would create pathways. Well, we know that the fracks don't travel those distances. We know that they don't travel more than about 600 metres. It's actually Refine's greatest contribution to the world of science to this date, is actually how far do the fracks travel. So if you're not going to get a frack that's going to travel several kilometres back towards the surface, you've got to think of what are the potential pathways. Now, one of those potential pathways is opening up a fault. So that's why we've looked at faults. One of them is that they actually get leaks on the surface. So it's nothing to do with the water coming back. It's the fact you've actually got to hold it on the surface, treat it on the surface, and that's where the leak and the spill is going to occur. Or it's because the well is failing. Because the water's coming back up, the fracking fluid's coming back, the flowback water comes back up the well, and the well is failing near its top. So that's why well integrity has become an issue, because it's one of the few potential pathways of getting contaminated fluid into the shallow aquifers. So the issues then, in that sense, the hunt for a conduit, a hunt for a pathway, has included what's the probability of spills and leaks on the surface of the water, what's the opening up of big conduits like faults, and what's the probability that it actually leaves the well as it comes back up. It's a well failure type issue. So the water quality issue, in that sense, our easiest way of looking into the water quality issue was to actually go hunting methane, because if the methane's coming back out, it means the water could come back out.
We've got a pair of questions conveniently located right next to each other there.
You mentioned the United States. You've looked at comparisons with the United States. Have you looked at other countries, particularly in Europe? Have any other countries started fracking yet?
Yeah, actually it turns out this has been a really, really useful thing when you're doing a European funding project. When the European funded project started, everyone wanted to work in Poland because Poland had the largest number of wells that were being fracked. For a number of reasons, Poland isn't actually progressing anywhere near as fast as the UK is. So it turns out that actually the best place to study fracking in Europe at the moment happens to be the UK, simply because there are about 3 countries that don't really have a moratorium. Every country has a slightly different position, but those that have drilled any form of well are the Polish, the Hungarians and us, more or less. The Hungarians have about 1, we have about, it depends on exactly how you count them, but we have several, and the Poles have about 40. So the Poles had the largest number, but they're not progressing beyond that initial 40, whereas our licensing round and regulations and planning rounds and whatever are progressing. And so in that sense, the activity at the moment is in the UK. Yeah. Other countries, for example, like France, which have some of the biggest potential reserves, have got a moratorium still in place. Yeah.
And let's take one last question from the gentleman next to you. Thank you.
This might be slightly outside your remit, but only slightly. Due to the fluctuation in the oil price worldwide, and it's very low at the moment, would we in the UK be better off to let everybody else frack, see what it does to the price, and then decide what we will do later?
The answer, yeah, I have the good fortune or the bad fortune, depending on what the oil price is, not to be a petroleum geologist. So at the moment, I have the good fortune not to be a petroleum geologist. 3 years ago, I had the poor fortune not to be a petroleum geologist. The answer is yes, of course, and that's partly why I say things like, I'm not the decision maker here. And the decision maker may be the politicians, the voters, but the decision maker is also the economists. And the oil price will make that difference. It probably makes slightly less difference than you automatically think, because of course there's a difference about, we're working in a national market and an international market. So we in the UK have a context in which we have a different energy makeup and energy security issue than, say, Norway. Now, Norway doesn't have the opportunity to frack, but you see what I mean, is the sense of that we can't just go, it would be a blunt instrument to talk about what the actual oil price is at the moment, the energy price, because there's a longer strategic issue as well, potentially in countries like the UK, where are we going to get our energy from? Now, also, of course, in other markets that have been a push, it's been a push to get away from coal. So we don't have so much capacity to remove much more coal. So we have a large number of gas-fired power stations. How are we going to feed them gas? So in that sense, there might be a different type of market in the UK. The Americans, for example, have used it as a way of potentially their coal prices dropped as a consequence. The world coal prices dropped as a consequence of having cheap gas. So you're never going to get away from the economics. And indeed, you can argue the present oil price is partly a factor of, people not liking, certain countries not liking shale gas and other countries not liking those countries that have oil. And it's an incredibly complex thing, and it's fascinating to watch. Fortunately, as I said, it's not my field. So you're absolutely right, you're not going to get away from economics, but the economics is more complex than just what is the price in that country, what's the price of Brent crude. Yeah.
Well, that's a very wide-ranging point on which to finish. I think at this point we better let Fred have a well-earned rest, go away and think about the politics and economics as well as the science of our energy supply. Thank you very much for coming and for your fantastic questions, and please join me again in thanking Professor Fred Worrall.